Properties of materials. Before the 19th century, most materials were used in a derivative of their raw state. However, since then, the scope of structural materials has broadened to include synthetics, polymers, ceramics, steel, and alloys. These innovations can improve the structural integrity of raw materials, such as these. Textiles, ceramics, and metals added to plastics improve flexibility, structure, thermal, or electrical properties. Steel added to concrete improves its flexibility and helps resist fracturing. Each type of material, whether it is a pure, semi-pure, or a composite, has its own molecular and conductive properties that react to burning, corrosion, degradation, freezing, and chemical reactions. Thermal properties, such as heat capacity, conductivity, expansion, and contraction of a material are important to determine how materials will respond under different environmental conditions. Metals. The term metal refers to any material, such as steel, that has high strength characteristics, conducts heat and electricity, and is machinable, hard, and lustrous. Metals lose electrons in chemical reactions, and because of this electron exchange, metal has good molecular integrity that makes it strong. An alloy is a mixture of two or more metals, and can include other additives or impurities to improve the tensile strength. Although all materials can change form in response to temperature changes, metal, particularly steel, is a primary material for weight-bearing structures because of its tolerance for thermal change. Metal alloys have a high tensile strength, but when they reach their elasticity limit, they begin to deform. If the load continues beyond the elasticity limit, the material will separate at the fracture point. Also, exposure to weather promotes oxidation, such as rust, in metals, which negatively impacts elasticity and tensile strength. Ceramics. Ceramics include several types of materials, such as rock, sand, minerals, clay, cement, glass, brick, insulation, and porcelain. Ceramic withstands extreme thermal, chemical, and pressure environments. Ceramics are mixtures of metallic and non-metallic elements, and the metal atoms easily lose electrons to the strong attraction of the non-metal atoms. Because of these bondings, ceramics have a high melting point and low corrosive action, and are chemical stable. Because of their low reactivity and relative strength, ceramics are used in highway construction, buildings, pipelines, cutting tools, and dams. In addition, many metal structures have a ceramic coating, called stress coat, that cracks at lesser strain levels than metals do. This allows engineers to see problem areas before they become points of failure. Organics. Substances that are based on carbon are called organics and can exist as solids, liquids, or gases. Wood, petroleum, natural gas, natural rubber, coal, collagen, and proteins are naturally occurring organic materials. Adhesives, plastics, nylon, and rubber are typical synthetic organics. Natural organics are responsive to most environmental conditions, such as temperature, humidity, and degradation or decomposition. As far as structural components go, you will see both natural, primarily wood, and synthetic organics, such as rubber. Synthetics and polymers. Synthetic materials are made by chemically connecting long chains of carbon molecules. Although organic molecules are resistant to sharing electrons, forcing them to do so creates a strong, stable material, called polymer. Some polymers, such as nylon, have a high degree of elasticity. Other materials, like some plastics, can be very elastic under a load force, but do not return to their former position after the force is removed. PVC is a common synthetic that is very rigid and stable over a long period of time. The behavior of polymers under mechanical force depends on time and temperature. Temperature negatively affects polymers, and deformation, tensile strength, and elasticity depend on the rate at which the force is applied. Fluid dynamics. Although water, which is a liquid, and air, which is a gas, might seem to have little in common, they are both subject to the principles of fluid dynamics. A fluid includes any substance that has no rigidity, lending explanation to why both liquids and gases are fluids. Although they both flow as fluids, they differ in other characteristics. A liquid has a definite volume, but no definite shape, and will change its shape to that of its container, but will not expand to fill it completely. On the other hand, a gas has no definite volume or shape, but a gas will change both shape and volume to completely fill a container. You should know these characteristics of fluids. Diffusion occurs when molecules of one fluid mix through the molecules of another fluid, motivated only by random molecular action. Cohesion occurs when molecules of the same type stick together. Adhesion occurs when molecules of different types stick together. These characteristics cause fluids to generate unique types of friction, which the following sections discuss. Specific gravity. To determine specific gravity, you compare the density of an object to that of water to get the specific gravity of that object. In other words, the specific gravity is the ratio of the weight, or mass of any volume of a substance to the weight, or mass of an equal volume of water. Measuring specific gravity lets you determine the fat content of milk, the purity of gasoline, or even the amount of charge in a car's battery. A hydrometer is the tool that measures the specific gravity of a liquid. One type of hydrometer is a long, narrow float with a graduated scale on the side and a weight at the bottom, see figure 7.22. The denser the liquid, the higher the scale sticks up out of the liquid as the hydrometer floats. Pressure. Pressure is the force per unit area and is measured in pounds per square inch (psi). If you have ever swum to the bottom of a lake or a deep pool, you might have felt like your chest and eardrums were being squeezed. In actuality, the weight of the water above you was pressing on you from all sides. By understanding this, you also understand that fluids at rest exert force. We can express this relationship between force and area as an equation, like this. Pressure, P, equals force, F/area, A. Or P equals Fa. At sea level, normal atmospheric pressure is about 14.7 psi, but this quantity changes with altitude, depth, and overall pressure changes. When you inflate an automobile tire to a pressure of 30 psi, you do not put 30 pounds of air into the tire. But the total force pushing outward against the walls of the tire, with a pressure of 30 psi, is about 12 tons over the entire tire surface.